All right, welcome back to Real Analysis. In this video lecture, we're going to look at two more sections of Chapter 1, Section 1.5 and 1.6, that are basically both about bounds on sets of real numbers. In Section 5, we'll talk about what I mean by a bounded set of real numbers, and in Section 6, we'll look at our final axiom, our final assumption that we're going to make about the set of real numbers that will prep us for being able to do our analysis. Okay, so if you're given a subset of the real numbers, say some subset called E, then there may or may not be some element that is bigger than or less than or equal to all the elements in E. Yeah, so when there is such an element, we call it a bound. And if it's bigger than all the elements in E, we call it an upper bound. And if it's less than or equal to all the elements in E, then we call it a lower bound. All right, so these are our two main definitions that are super important, and I encourage you as we learn this material to kind of develop some kind of either index card or glossary system, internalize these definitions, write them down somewhere, and have some way where you can refer to them, because the proofs that we construct will have to be done using careful applications of these definitions. Okay, so the first one's definition 1.1. I'm defining what I mean by an upper bound. So it's defined for a set of real numbers that's called E, and the author is denoting it by the number M. And M is called an upper bound. So the italicized font in your text is the term or word or more sequence of words that are being defined. An upper bound for E is a number M that has the property that X is less than or equal to M for every single X in E. All right, so notice that an upper bound is defined in terms of a universal quantifier. A number M is an upper bound if it does something for all X's in E, and in particular, if it's greater than or equal to it. Okay. Conversely, I'll sort of switch colors so it doesn't look so monotonous. A lower bound, that's a number, the author's denoting it by lowercase m. So it's a lower bound for the set E if it's less than or equal to everything. Again, that's for every X in E. Okay, so an upper bound is a number that's greater than or equal to everything in E. A lower bound is a number that's less than or equal to everything in E. All right, just some sort of remarks about this. To continue the terminology, I'll call a set E bounded if it has both an upper and lower bound. So a bounded set of real numbers is a set of real numbers that has both an upper bound and a lower bound. Okay. Uh, Upper and lower bounds for a bounded set are not unique. In fact, if your set has any upper bound, if you take a set with an upper bound, then any number that's bigger than that would also be an upper bound. Same thing for lower. If you gave me a set that has a lower bound, I could take any number that's smaller than that, and it would also be a lower bound. So when a set has one of these things, it actually has infinitely many of them. You can choose any number larger than any upper bound, and it will also be an upper bound. That follows from the transitivity of our order on R. Let's look at an example. So I'm going to look at this first example here. I'm going to take the set E to be the open interval from 0 to 1. We're going to use that familiar notation. Here I'm writing it in so-called set builder notation. So we'll use this when we're trying to precisely describe subsets of the real numbers. By this open interval from 0 to 1, I mean those elements of the real numbers that are strictly bigger than 0 but strictly less than 1. Okay, so that set is bounded. In particular, it has an upper bound. The number 1 is an upper bound for that set. 1 is an upper bound for that set. Well, because by definition of the set, for any X in the set, 1 is greater than, and hence greater than or equal to that number. So is 2. In fact, any number bigger than 1 is an upper bound for that set. Right? You can stop the video and think about corresponding statements for lower bounds. The set E also has lower bounds. Maybe you could stop the video and say what one of them is. Maybe you can say what a couple of them are. Here's a slightly related set. It's the closed interval between 0 and 1. So I'm looking at the X's in R that are greater than or equal to 0, but less than or equal to 1. 1 is also an upper bound for that set. So is 2. Notice that 1 is actually even an element of that set, right? So one of the points of this example, this pair of examples, is to point out that sometimes a set has an upper bound that doesn't belong to it, The number 1 in the first example, E1, is, sorry, 1 does not belong to the set E1. It's not in there, but the upper bound down here does belong to the set E1, E2, sorry. All right, so my tongue is tripping all over the place, but what I'm trying to say is that an upper bound for a set may or may not belong to that set. All right, so we're going to give some language for the case that when it does. So some more definitions. 2 new entries in your what will be a very large stack of index cards. So I'm going to call a real number a maximum for a set E. So the number m is called a maximum to the set E if it's an upper bound that belongs to the set E. So there's a number m that belongs to E, and it's greater than or equal to every other member of E. So the author's writing larger here for every other, but M is greater than or equal to every X in E, and it belongs to E. And it's called a maximum. Okay, if E has a maximum, we're going to use this notation. We'll just write max of E. So I encourage you to think of this as a two-part definition. So first of all, the first part is that the maximum has to belong to the set E. The second condition is that that maximum is greater than or equal to X for every number X in E. All right, so an upper bound that belongs to the set is called a maximum. Likewise, a lower bound that belongs to the set is called a minimum. So you have a number m that belongs to your set E. It's smaller than every other member of E. It's called a minimum. Okay, and it's denoted by MINE. So minimum and maximum. Two notions related to bounds. If we go back to our example above, we were looking at this open interval from 0 to 1. We said it's a bounded set. It has an upper bound and a lower bound, but it has no minimum or maximum. Maybe you should stop the video and kind of think about that for a second. So whereas the number 1 is an upper bound for that set, it doesn't belong to it. And in fact, any number that belongs to that set E1 is not an upper bound for that set E1. You know, for example, like take the number 0.9. Well, 0.99 is bigger than that and still in the element in the set E1. Yeah, so this is kind of one of the natures of sets of real numbers. That set E1 is bounded. It has an upper bound, but it doesn't have a maximum. Our closed interval, E2, it's a bounded set. It's got the same upper and lower bounds actually as E1. The same upper and lower. Any number that's an upper bound for E1 is also an upper bound for E2, not vice versa. But E2 does have a maximum element. It's equal to 1 because the element 1 belongs to the set E2. Yeah, it's got a minimum element as well, 0. Cool. Right. As a sort of different nature example, if we look at the set of natural numbers, the set of natural numbers is not bounded. Right? There is no number that's greater than or equal to all the natural numbers, so it's not a bounded set. It is so-called bounded below, right? So that means it has a lower bound but no upper bound. So it's a not bounded set. It's not a bounded set, but it does have a lower bound, so I'll say that it's bounded below. In fact, it even has a minimum. The minimum element of the set of natural numbers is the number 1. 1 is a natural number that belongs to a set of natural numbers, so it's its minimum. Here's a place for you to kind of stop the video and create something. Examples like this aren't unique. You can create lots of different examples, but can you create a set that I've got kind of 3 criteria here? I'd like it to be bounded above, right? So I want it to have an upper bound, but not bounded below. So I don't want it to have a lower bound, but I don't want it to have a maximum. So I don't want any of its upper bounds to belong to the set. So you can stop the video. I hope you will stop the video and kind of think about something. There's lots of ways to produce such a set. I think I'm going to go for something like this. I'm going to take E to be the set. In interval notation, I would maybe write something like negative infinity to 0, and then make it an open interval. So you're familiar with interval notation, I know, but let me write it in set builder notation. I'm talking about those real numbers called x. And then the criteria on x is just that they're strictly less than 0. Okay, so that set is bounded above, because if I say take m equal to 0, that's an upper bound. By definition, yeah, I specified that E was the set of numbers that are less than 0. So 0 is greater than all elements of E by definition. So it's an upper bound. It's not bounded below. There is no number that is less than or equal to all elements of E, because E contains all negative real numbers. So my set E here is not bounded below. If you give me any potential real number m that you think is a lower bound, I could subtract 1 from that number and find an element of E that was less than it. So it has no lower bounds, but it doesn't have a maximum. It doesn't have a maximum because 0 doesn't belong to E. Okay, hopefully you created some different example. There's lots of them. Cool, just getting used to the language here. Okay, so continuing into section 1.6, it has kind of an exotic, strange sounding name, soups and imps. Those are shortened versions of the words supremum and infimum. So let me try to tell you what I mean by that. Okay, so just to kind of recall, I'm going to stick with maximum, but you should stop the video and kind of write the corresponding ideas for the minimums. Let's recall that a number m is a maximum for a set E if it's sort of a two criteria definition. First of all, m has to belong to E. Okay, so it's required. A maximum element of a set is always an element of that set. And then the second condition is that it's also an upper bound. So a maximum element is an upper bound that belongs to the set. Okay, so for every x in E, x is less than or equal to m. So it's a maximum element is an upper bound that belongs to the set. All right. So in particular, if you took some other, I'm just going to decorate the m. If you took some other element called m bar, and it's some other upper bound for E, well, then it would have to be greater than or equal to our m. Why is that true? That's true because m belongs to E, and an upper bound is greater than or equal to all elements of E. So in particular, it's greater than or equal to m. Okay, so this maximum element is one way to say it is it's sort of the smallest or the least of all upper bounds of the set E, right? M is the least of all of the upper bounds. So going back to one of our examples, if we take E to be that open interval from 0 to 1, we already said it has no maximum element, but it still seems to have like a least upper bound. The number 1, right? Number 1 is an upper bound, so is 2, so is 1.1, 1.001, has infinitely many upper bounds, but there's sort of the smallest one. If you take any number less than 1, it's not an upper bound anymore. Okay? You could also stop this video. You should stop the video, kind of think about everything I'm talking here in terms of minimums and lower bounds. My set E also doesn't have a minimum. But the number 0 is sort of the greatest of all of its lower bounds. Yeah, so there's these, doesn't have a maximum, but it does have an upper bound, and it kind of seems to have a least upper bound. It's 1. It also doesn't have a minimum, but it does have a lower bound 0, and 0 seems to be the greatest of all those lower bounds. If you tried to increase from 0 at all, you're not going to have a lower bound anymore. Right? There's some nice imagery we can draw, but I think I'll wait and do that maybe in the class. So that's supposed to motivate the following terminology. All right. So we're going to call a real number a least upper bound, or a synonym supremum, for a set E if it is the least of all of the upper bounds for the set E. Okay, so you take some set of real numbers that's bounded above and non-empty. These are the kind of preamble details. So I've got a non-empty set of real numbers that's bounded above. Then the smallest of all of those upper bounds is called the least upper bound of E. Yeah, so it's a nice name, least upper bound. It's also called the supremum of E, and it's denoted just by truncating the word supremum, and I'll pronounce that sup E. Okay, so that's what I mean by the sup of a set. The sup of a set, supposing it exists. There's no reason to think that it should, but I'm just making a definition. The sup of a set is the smallest of all of the upper bounds of that set. Okay, the definition only makes sense if the set is bounded. Right, I'm going to underline that in red just to emphasize it. If the set's not bounded above, then it doesn't even make sense to speak about its supremum because it doesn't have any upper bounds at all. Flip side of it, stop the video and let this soak in, but it's the greatest lower bound, or the fancy word is infimum. So you have to have this time a set of real numbers that's bounded below and non-empty. Okay, it's bounded below and non-empty. Again, those are part of the conditions. If you're not bounded below, you don't have any lower bounds, so I can't talk about the biggest one. But if you do have lower bounds, then I can define little m is the greatest of all of them. I'll call that the greatest lower bound. It's got a nice name. It tells you what it is. The fancy word for it is infimum. And you write it like that, I-N-F, and I'll pronounce it imph. Imph of E, short for infimum. It's the largest of all the lower bounds of E. Okay, once again, just to emphasize, it's only defined for non-empty sets that are either bounded above, in the case of the supremum, or below, in the case of the infimum. This book seems to want to enlarge the language, so some kind of pesky details. If you break any of those rules, if your set is empty, then the author can define the infimum of the empty set to be infinity and the supremum of the empty set to be minus infinity. Kind of makes sense. Let me pick on the supremum part, that the empty set, well, every number for it is an upper bound. So the greatest upper bound should be minus infinity. It's just kind of an intuitive idea. Minus infinity is not a real number. Okay. Likewise, if E is not bounded above, we can say that its supremum is infinite. If it's not bounded below, its supremum is negative infinity. But I actually happen to prefer to be in the camp that if E is empty or it's not bounded above or below, I just say that the supremum and the infimum are not defined. All right. So the author kind of wants to have this larger language, but for empty sets or sets that aren't bounded, we'll just say that their supremums and infimums don't exist. Cool. It's maybe surprising. It's not surprising, actually. If you stop the video and draw some pictures, any subset of real numbers that you define, that you draw or think about, that has an upper bound has a least upper bound. Likewise, any subset of real numbers that has a lower bound has a greatest lower bound. So any non-empty subset of the real numbers that's bounded, yeah, so it has lower and upper bounds, well, it has an infimum and a supremum. All right, but you cannot deduce that. You cannot deduce this from our axioms. It's not possible to take the order axioms and the field axioms that we gave above and prove that a non-empty subset of real numbers that's bounded above has a least upper bound. We have to take it as an axiom, the way we're approaching this. Okay, so we're going to call that the completeness axiom for the real numbers. And this will be our last sort of assumption that we're making. We'll be able to do all the analysis that we want to do with those field axioms, the order axioms, and then this guy, the completeness axiom. And I already said what it says. It says that if you take a non-empty set of real numbers that's bounded above, it has a least upper bound. From this, we can deduce the corresponding fact about infimums and lower bounds. So that's why it's missing. But the completeness axiom says that if you have a non-empty set of real numbers called E, and it has an upper bound, then it has a least upper bound. Okay, so if it's non-empty and bounded above, the sup of E exists and is a real number. From this, we can prove that if it's bounded below, the inf of E exists and is a real number. It's going to be part of the exercises I'm going to ask you guys to think about. Okay, so the completeness axiom that any bounded subset of real numbers bounded above has a least upper bound. Let's think about these sups and imps in a couple of examples here. So I'm going to write some sets E, and in each example, what I'd like to do is say what its sup and its imp are, if they exist. Okay, if they don't exist, we'll say that, and then we can ask the question, does E have a maximum or a minimum? So in the first example, part A here, it's a finite set. The set E has 4 elements in it, -3, 2, 5, and 7. That set is certainly bounded. Yeah, every element in that set is less than or equal to 7, but greater than or equal to -3. Yeah, so those are upper bounds, and those elements actually belong to the set. Yeah, so we can say right away that the maximum of this set E is the number 7. The minimum of this set E is the number -3. Those elements belong to it. If you want me to use the definition, say to expound on this, 7 is an element of E. Okay, that's the first part. And X is less than or equal to 7 for every other element of E. I can prove that by looking at them. 5 is less than or equal to 7, 2 is less than or equal to 7, and so on. Similarly for the minimum. Okay, so 7, by the way, it's the maximum, it's an upper bound, and it's certainly the least upper bound. Yeah, if you take any number that's smaller than 7, then it's not an upper bound for the set E anymore because, well, it's smaller than 7. So these things, the maximum in this particular case is also the supremum of the set E. The minimum is also the infimum of the set E. And I'm going to ask you to think about this on your own and in the exercises, but similar statements could be made about any finite set of real numbers. Every finite set of real numbers is bounded. It contains a minimum and maximum element, and those would be the supremum and the infimum of the set. Okay, any finite set, any non-empty finite set of the real numbers. So not just this one. Here's a slightly more interesting example. Let's take a look at the set of real numbers x, whose squares are strictly less than 4. Okay, is that set bounded? Is that set bounded? I think it is. That set is bounded. And notice that if you take a real number that's, say, greater than or equal to 2, then using our order axioms and some of the business about algebraic axioms of R, we could prove that its square was greater than or equal to 4. Okay, so what a kind of contrapositive of that is that if an element belongs to this set E, then that element is strictly less than 2. So if X is an element of E, then X is less than 2, right? So 2 is an upper bound. Right? Likewise, I'll let you think about the details. -2 is a lower bound. -2 is a lower bound for this set, right? Not only are those things upper and lower bounds, they're actually equal to the sup. 2 is the sup of the set E, -2 is the inf of the set E. Because again, our calculation, let me pick on the sup part. If you pick something strictly bigger than 2, its square will be bigger than 4. So it's not an element of E. Yeah. So this number 2, it's an upper bound for the set. And maybe I said that a little bit confusing. Maybe the best way, if you take any number smaller than 2, then its square will be less than 4. So not, well, here, I'm sorry, I'm being a little sloppy. If you take any number smaller than 2 and bigger than -2, then its square will be less than 4, and so such a number can't be an upper bound. It also can't be a lower bound. Right, so I'm maybe not being quite as rigorous as I'd like to be, but the infimum and supremum of the set E are the numbers -2 and 2. E has no maximum and minimum. It has no maximum and minimum because that least upper bound 2 doesn't belong to the set. Any element that does belong to that set, you could make that, you could take something slightly smaller or bigger than it and also belong to the set. So it doesn't have a maximum or a minimum element. Let's look at one more. This time the set E is the set of real numbers x that have the form n over n plus 1, where n is a natural number. Right? We could list out the elements of this set if you like. Taking the natural number equal to 1, you get the number 1/2. Then you let n equal 2, and you get the number 2/3, and so on. So that's an infinite set. That set is bounded. Yeah, every element of the set E is, well, greater than or equal to 1/2, but less than 1. Right? N over n plus 1 is never going to exceed 1. So we can say the infimum of this set E happens to be its minimum element. That's the number 1/2. Right? You can check the definitions to verify this stuff. The supremum of the set E, the least upper bound of this set E, I don't claim this is obvious, but I'm just going to claim it anyway here. It's equal to 1. 1 is an upper bound for that set. It's certainly greater than or equal to everything in that set. But any number less than 1 cannot be an upper bound. We'll develop some tools to develop or to justify these remarks, but I'm just trying to get you warmed up to these definitions. The set E has no maximum. So make sure that you kind of stop and digest this stuff that I'm claiming. The set E is bounded above. It's bounded above by 1. In fact, 1 is the least upper bound. It's the supremum of the set. But the set E doesn't have a maximum element. It's because 1 doesn't belong to E. The supremum doesn't belong to the set E. Cool. Okay, I'm going to finish this lecture. We're about 29 minutes into it. I like to kind of keep these things to about a half an hour, and we can fill in details in class by looking at an example that's sort of like one of the exercises I'm going to ask you to do in your homework. Suppose I take a non-empty set A, and it's bounded. So I have a bounded non-empty set of real numbers, and then I define the set B to be the opposite of all of the collection of negative x, where x is an element of A. All right. So A is some bounded set of real numbers, and B is the collection of additive inverses, the opposite, the mirror image of the set, if you like, across 0. So what I'd like to show is that if M is a maximum of A, so it exists and is a real number, then its opposite is a minimum for B. All right. In the exercises in your text, they phrase this a little bit more open. The author would say something like, find a relationship between the maximum of A and the minimum of B and prove it. All right, so here the relationship is that they're opposites of each other. The maximum of A is the opposite of the minimum of B and vice versa. So to walk you through the proof here, it's just kind of a sea of definitions. If we take some subset of the real numbers and we call its maximum A, well then first of all, every element of A is less than or equal to that maximum, right? So by order properties, the opposite, negative x, is greater than or equal to negative m for all x in A. And that means that this number, negative capital M, I'm calling it lowercase m, it's a lower bound for B by definition, right? It's less than or equal to all elements of B. An arbitrary element of B looks like negative x, where x is an element of A, all right? And then moreover, M belongs to A, so by definition, negative M, negative capital M, lowercase m, belongs to B. So I've got a lower bound for B that belongs to B, so that's its minimum by definition, two-element checklist. Okay, so I'm going to end the lecture there, and thanks for your attention.